So today I will talk about work that I've been done at the end of last year and then refreshed throughout the summer, which is trying to rewrite the value numbering we are using in FRE and PRE, mainly for the motivation to make it work on regions. So why? Because we in a lot of places in the compilation pipeline we'd like to perform some basic cleanups because our code generation, like we do in the vectorizer, isn't perfect. So this, for example, the vectorizer leaves around redundant induction variables, it leaves around redundant loads sometimes. For example, in the unroller, when we unroll an inner loop, we want to decide if we want to unroll the loop containing the unrolled loop, but to compute meaningful estimates for the size growth, we want to clean up the unrolled code before trying to estimate the size effect of unrolling the outer loop containing that, the just unrolled loop. So what is the existing state is basically most passes don't do any cleanup. They just rely on the particular pass ordering that eventually there will be a pass cleaning up after me. Most passes try to remove code they are making dead. The most commonly used cleanup thing is the Cfg cleanup. So basically passes do not bother to remove edges or basic blocks, but just make the controlling conditions true or false, and then run the Cfg cleanup, which will remove all the no longer reachable code. Then there are various attempts to improve code generation to not cause any of the cleanup requirements, like the vectorizer has some hash tables to do some very poor man's CSE when it generates expressions. This is actually able to remove about half of the induction variables it otherwise would create. Then the unroller, the case where I talked about, it has its own mini pass doing constant propagation on the just unrolled body, because this is just to, well, make obviously dead code dead by propagating the now constant induction variable evolution in the unrolled bodies. And for example, the vectorizer runs conditionally a dead code elimination pass after it runs. So if the vectorizer is enabled, there will be a dead code elimination pass right after it. Sorry, just wait until people are set. And yeah, what's the problem with this? This is, of course, always an issue in follow-up passes that are confused by that code, are confused by not optimized code. This requires us to carefully schedule passes. For example, after our loop passes, we lack a real pass doing CSE on memory. There's a late DOM pass, but DOM is only so good at doing CSE of memory. And then, of course, there's always the idea, well, I just schedule another FRE and other DCE pass everywhere where possibly necessary, but it, of course, explodes in compile time. Or
the problem is also that you can disable passes as well.
Yeah, but if users disable passes, well, then they are on their own. If they still expect things should still work correctly, but otherwise the optimization result maybe not be optimal. And so we've somehow gone the route doing these like mini passes in the unroller or CSE in the vectorizer, but it's not really a very maintainable thing to do. So we have made it where it's really important to do and where there was no other short-term solution. For example, for the vectorizer, I think Bin Cheng has implemented some prototype on making the DOM CSE callable on a single basic block. but this never ended up in mainline. So the motivation is we want to have something that we can throw on a region of code. Yeah, so we want something generic, and this something generic should also be powerful enough. So for example, the existing mini pass in the unroller, it just does constant propagation in a very imperfect way. If you look at the actual implementation, this isn't really enough. So what are the options? The options is, of course, make existing stuff work on smaller regions. As I said, Bin has prototyped this for DOM, or we could use stuff like propagate constants for unrolling from the unroller and enhance that, or of course implement something new. This is usually our preferred implementation choice. Add something new. So I chose to add something new. It's also more fun, right? But actually I didn't really want to add something new. I wanted to replace whatever we have with the something new, so that we don't end up with more code, but eventually with less. This is the wrong slide. Wrong. Yeah, this is the right one. So I decided to tackle multiple issues at the same time. We do have a quite powerful CSE pass, which is a FRE and PRE, which uses the SSC-based value numbering, which has gotten a lot of tricks, especially when working with memory over the last years. And I tried to address some issues we've run into with the approach taken by that pass, and basically rewrite the existing value numbering pass to work on regions and fix those issues on the way. One of the issues is that the SCC-based value numbering does expression simplification while it does the value numbering on expressions of values. And its values are just SSA names, which means when it looks up definitions of SSA names to combine multiple value expressions, it gets at information we attach to SSA names like ranges that may actually not be valid at the point the simplification result is used. And we've worked around that by carefully clearing this kind of information, storing it somewhere else, and then restoring it after the value numbering, which has worked out so far. At the beginning of this year, there was a new bug where I saw that approach break down. So it's actually not going to work in the end. So the better idea is, of course, to work on on the real expressions of SSA names that are actually available at the point we are trying to use the simplification. So this is one of the design goals. And then SSC, the SSC-based value numbering is an iteration scheme, but it iterates on the SSA cycles, so basically on phi nodes with incoming backetches. But it isn't really optimistic in the CFG, so it cannot consider initially all edges as not executed, but it considers everything executed. So usual cycles don't get optimistically value numbered because you have the back edge with a value that you didn't see in the first iteration. And the controlling condition, so you can't really reliably figure out that an edge is not executable, and by that means optimize the iteration result. So if you have a loop that actually doesn't iterate because the exit condition is always true in the first iteration, the SCC-based value numbering will still iterate the phi node of the induction variable and will compute it as varying. Even if it later eventually figures out the and it won't figure out that the exit test is not taken. So that's quite lousy for a scheme that is iterating. So I actually improved the SSC value numbering in the last years to handle some of the cases by carefully ordering in which order we process the SCCs. So hopefully we get some of the conditions computed to always false before we actually need to look at the baggage thing. But so the idea was to go over to a scheme that is optimistically in the CFG, so that we can really assume all edges are not executed at the beginning of the iteration. And the current SCCVN doesn't have a mode where it doesn't require iteration, which would be really nice for cleanup phase, where you eventually don't want to spend compile time on trying to be optimal. So, yeah, so I didn't really want to rewrite the whole value numbering. So I decided to just focus on changing the iteration scheme, and I left all the hash table handling, the expression simplification code, I left that in place, and just changed the iteration scheme from visiting SCCs of SSA names to one that does basically an RPO walk of the CFG and iterates on that. So as I said, I wanted this thing to work on regions to be able to use it as cleanup phase. So for example, when the vectorizer is finished running, it could run the value numbering on the vectorized loop body. And of course, when you have something that works on a region, it should also be of compile time complexity of the size of the region and not something bigger, because otherwise it's not really region based, I would say. So the API I ended up with is the do RPO VN on the function containing the region, one entry edge and multiple exit blocks.
The exit blocks are still in the region? Or
no, they are outside of the region. Yeah. So it's basically, I want to handle natural loops with multiple exits. It actually returns whether you should run Cfg Cleanup at some point if you want to look at the IL again, and it should be valid, because I also do not remove edges or basic blocks, but just turn conditions into always true or false if they turn out that way. And I do not do elimination in the not executed parts. That means the not executed parts in the L could still use released SSA names. So the SSA form is not strictly valid in the never executed parts of the program. It does handle regions that do not have exit fees. So if you have uses of SSA names that are defined inside your region, but the users there are users outside of the region. The definitions, if they would be eliminated, they remain as a simple copy inside the region. So I do not do elimination outside of the region. The other way to fix that would be to require exit fees. But I thought that's most simple. If there are exit fees, elimination is performed on the exit fees, but not in the exit blocks. So if you have exit fees, there are no copies remaining. But if you don't have exit fees, then you get just the copies remaining to keep the definition live, because it's still used. So the code is now on trunk, and there's currently a single user of the region API, which is the loop unroller. So I removed this mini path doing the constant propagation and instead do as it do value numbering of the containing loop body when a loop was unrolled or peeled. So that basically when we then try to decide whether to unroll that containing body, we have a good estimate of its size of the body. And this actually allowed me to remove one extra param we had on the Calculix Fortran test case in the test suite, where we had artificially bumped the number of maximum unrolled instructions by a factor of 2, and I no longer need this bumping by a factor of 2, but we get the desired unrolling because of the better estimates we now do. It actually didn't make a difference in the spec benchmarking, so I'm not sure why or. So I'm not sure. So the original reason for the param in the test case said, oh, do it consistently, because some targets lowered this limit, but then the test case number stayed, but Honza dropped the global limit. So it's basically, it was at the old limit, and now it also works with Honza's dropped limit, which means the drop limit is also applied on the spec benchmarking. So the latest level unrolling wasn't probably that important for the compiler, for the speed. So I'm not sure. At least the unroller behavior changes for that test case. And of course, other current users are now FRE and PRE, because the SSC-based value numbering iteration scheme is gone. So there's only the RPO one left. There are some future possible users. As I thought, the vectorizer could probably use this thing on its body, because, yeah, it could use it on its body. Also, the SLP vectorizer could eventually revalue number the basic block of the whole basic block of the affected basic blocks, because we do have some PRs which say that DOM, which runs after SLP vectorization, cannot handle some of the redundant memory things, because it doesn't handle the view converts, and it doesn't handle piecewise loads and stuff like that. And yeah, we have some open PRs for that.
But should we tease that code eliminates the basic blocks first before we do this? Because we keep most of the scalar statement inside of the vectorized loop.
Yeah, I think that's the reason why the vectorizer runs the conditional DCE. But I thought Richard had patches to fix that. I'm not sure if that's, so Richard is not here, the correct Richard. But yeah, I think we need to see where it makes sense to run this kind of cleanup. I mean, the cleanup itself is of course more expensive than for example, the simple constant propagation, but it's run in the non-iterating way, so it visits each statement exactly once. But of course, for the memory handling, it does use the alias walks, but only up to the region entry. So I think it's a reasonable amount of work that is done. Other possible users is jump threading. Currently, the jump threading is piggybacked on DOM and DOM's value numbering engine. So when jump threading duplicated the path, we could run the cleanup on the no isolated path, similar probably to for the path isolation, the path, how it's called, the late path thing, path we have. That's already again. So when I replace the SCC-based value numbering with the RPO iteration-based value numbering, I'm not really replacing equivalent kind of transforms. As I said, the SSC iterates the SSA cycles, and I'm now iterating CFG cycles, which makes it, in some cases, quite more expensive than the SSC iteration, because CFG cycles are more naturally appearing complex than the SSA cycles. So I chose to switch the value numbering to the non-iterating mode at 01, which makes it faster than the previous implementation for 01, and use the iteration only for 02 and for PRE, which also only runs at 02. So for when I looked at the compile time for Spec 2006, there is a single file inside, I think it was GEMS, some Fortran thing, where compile time increases about 10%. That's the worst thing. Otherwise, it's about 2% if it's measurable or in the noise. So it really depends on the loop depth you have, because the iteration scheme assumes the back edges are not executing, and you're figuring out one back edge per back edge that it is executable, basically. So, yeah, what are the good things, the features? We can handle the CFG cycles optimistically, which actually helps if you have irreducible regions. I've seen quite some test cases where the value numbering can make them nicely reducible in one go, while the SSEVN based iteration, it usually does nothing to any of the conditions inside the loops. And it also achieves the goal of doing the expression simplification on SSA names that are available at a given statement, which means we can retain the range information, which means we can do more expression simplification. This plays also nicely with the idea to eventually, in addition to the regular value numbering lattice, keep track of value range lattice in parallel during the iteration, which means we'd have context-based ranges, and we could use those range information when simplifying the expressions. So yeah, iterating the iterating mode is usually slower than the old implementation. I did add a param and some to limit the maximum loop depth it would consider handling optimistically. Just, well, I think I set it now at 7, which doesn't help this single Fortran file. If I set it at 3, which is, I think, unreasonably low, then I get the compile time reduced to the penalty to 2% compared to the 10%. So I've bumped it up to see what else code in the wild will go too slow and what we need to do about it. So most of the time is, of course, spent in the alias walks, because the rest of the value numbering machinery isn't really expensive. So it's doing the repeated lookups for all loads and stores. That makes it expensive. And so in addition to the value lattice itself, it also tracks during the iteration availability. So what SSA name is available for a given name. It does this during the iteration, mainly to have this information available when it does the expression simplification. So this is also a part that makes, in principle, it makes the iteration a little bit more costly. But it also makes it possible to do, in the non-iterating mode, to do the elimination in the same walk of the IL as I do the value numbering itself. So like DOM which basically looks at each statement, sees if it's available, and then it optimizes the statement. And the non-iterating mode does the same. It looks at each statement exactly once. So, to do. So before committing, I did some late cleanups, and it turned out that some of them were not a very good idea, and I made it nice, and nice is not always best. So our regression hunting people found a lot of bugs, and I ended up fixing them, and I needed to dump down the non-iterating code paths to even visit known not executable blocks, which is of course not something that I like. I have a work in process patch that I didn't want to commit before Cauldron, but only after, that restores the property that we don't need to visit the statements that we know are not executable. So it basically decouples the non-iteration walk over the CFG from the iterating mode and doing a greedy walk, just considering executable edges, but ordering the basic blocks it visits in RPO order. So yeah, and it turns out it now works nicely. Until I commit it and the regression people come up with new test cases. This is why I didn't want it to commit it before Cauldron. It also now really helps if you do the Bootstrap 01, because it runs into a completely different path now, doing the value numbering. This is something I broke with the late nicely cleanups. Before I always did the Bootstrap 01, for those I didn't. Yeah, I wanted to experiment with adding a value range lattice, because I think, for example, doing the early optimizations, it really helps if you can eliminate all the conditions that are not true. And we do have the early VRP pass, but that kind of requires you to clean up the memory loads first, and at the same time, the value numbering would like to know paths that are not executable. So doing this at the same time sounds like a good idea. And I think it will work out nicely in the non-iterating mode. If it will work out nicely in the iterating mode, I have to figure out, or if it's ending up too costly. So yeah, I want to play with that a bit. Possibly not.
Do we do any VRP at 01?
No, currently not. But why not? Yeah, I want to use the range-based API from more places. Like I said, had some examples in the beginning of the talk. I'm not sure if the VRP or use for more places are going to happen for GCC 9. I guess if there's a motivating, obvious case, then yes. Otherwise, we can just wait and see and iron out the bugs in the state where we can easily roll back to the old SCC-based value numbering. I do want to get rid of the other value numbering we have. So I think Jeff split it out to the Gimple SSR scoped tables, which does the basically expression hashing and stuff, expression comparing. So yeah, Jeff wanted to remove the jump threading from DOM somehow, so disentangle this, and then DOM would be left as just one non-iterating CSE, and we'd have a non-iterating CSE then, which we could use in place of that. But it's probably also GCC 10 work if Jeff isn't faster than I think. But he seems to be busy with string length warnings and stuff. And I definitely want to look at improving compile time. Most of the compile time of FRE, even before the new iteration scheme, is spent in the alias walks. And there are some ideas that can be done to address this. Yeah, for example, DOM is a lot better here because it only handles exact equivalences. It doesn't have fancy translating through memcopy and whatever. So it just puts things in the hash table without context, and so it can do a hash table lookup. If it finds something, it then does a check for validity. Can I use this? And within the value numbering, the other framework, you're basically doing, oh, let's see if we have this expression. No, look at the next place, at the next definition where I have a different memory state. Look again, up until to a point where I know, oh, the memory state is affected in a way that I can't look across that. So we are doing very many lookups without knowing if there is possibly a memory reference that could have useful information. So one idea is to kind of hash base objects whenever we see a definition. So we can do a quick lookup. Is there a base object we could reach? And if not, then we don't need to do any fancy walks. But eventually, there will always be a base object that will be in the hash. So one needs to do experiments, do some statistics, if that's a solution that would end really up doing less work. Then currently the alias walks. So now that we have we track the executability of edges optimistically, and we can rely on the executable edge flag, we can eventually skip regions we don't need to process with the alias walks. So currently the alias walk only uses virtual operand value numbering to eventually not visit two paths from a fee node, but only one, or just skip it completely if value numbering decided to value number the virtual operand to something. For example, if you have a merge fee and you get two virtual operands in and one edge is not executable, value numbering will value number the result of the fee to the single executable edge value. And then the alias walk will not walk the non-executable region, but only the executable one. It doesn't work if you have three incoming edges and one is not executable, because there's no, it will be varying, and the alias walk will walk all three. So that's something that can be done, but it probably won't end up speeding up things very much, because usually edges don't end up not executable. Then there's something one could do. There's a slight complication, like if we have a load and in the first iteration we figured out, well, there is nothing we can reuse, then by definition in further iterations we may not figure out, oh yes, there is something, because that would go in the wrong direction in the lattice. But we still do all the lookups and try to prove again that we really didn't find anything. But of course we have to put the expression into the hash table, and currently we are putting it in the hash table with the memory state that is associated with the farthest statement we may translate it up to, which is actually useful for PRE. Before I left for the Cauldron, I started a test suite run and pruned out this feature. There isn't any fail because of that, so we have no test suite coverage, which could ask for, oh, well, okay, just remove this feature and then we can do this trick. Or we can somehow remember with the statement flag, did we record something? So is there a memory state we have translated to? But if not, then the alias walk would also be cheap, because we would run into an aliasing statement in the first lookup. So we probably then don't save very much. So it again needs some statistics, what could be the possible benefit. So yeah, it needs some, so definitely the cost is in the memory statement handling. but it needs some more thought how to speed it up and more experiments. But I want to spend some time doing stage 3, speeding this up. So let's see. Questions.
Could you maybe spell out what the SSC abbreviation means? Like, what is SSC value numbering?
It's a strongly connected component. So basically, it finds cycles in the SSA graph, and it value numbers all statements that define the elements of the SSA cycle by just visiting them all over and all over again until nothing changes in the lattice. So basically, if you have an induction variable, it will have the phi node merging the value over the back edge with the value from the loop entry. Then it will have the increment, the induction variable increment, and this is the usual 2 parts of the strongly connected component for an induction variable. Or for GCC, we have SSA form for memory. Basically, each definition acts as a new definition for the memory SSA symbol. So in a loop, you're basically collecting all memory statements over the phi node merging the state over the back edge and states from the entry. So the SSC-based value numbering will visit all memory loads and stores and iterate over them all the time.
Just out of curiosity, since your definition of a region is a single entry and multiple exit, presumably something like an extended basic block, why do you have to consider back edges at all? As in, why do you need your algorithm to make a choice between iterating and non-iterating if there are no back edges in your region?
If there are no back edges in the region, the schemes are equivalent.
Right, okay.
Yeah, but so you could have just a region, and then there's a loop inside, and then you have exit after the loop. There would still be a single entry, single exit region, but there's a loop.
But there's a loop within the region, right?
Do you have any information how much CPU time hash table consumes? Because you use hash tables for value numbering.
Well, I can tell you that we have the time bars, right? So we have a time bar for the alias walking code, and the alias walking code includes the hash table lookups for basically the hash table lookups that are done on the previous memory states, and the time spent in these things is like 95% of the value numbering. If you look at profiles, the thing that pops up is the get ref base and extend, basically analyzing our generic memory reference trees. The white int thing when you multiply the sizes in our great representation. So this is the thing that pops up, but it's all contained in these alias walks thing. So the hash tables itself. So if you have code without memory, I didn't look at profiles there, but I guess then you would see maybe the hash tables, because that's really the only thing that's left then, right?
I am asking this because hash table in GCC is not optimal. So there are possibilities to improve hash table. Because, for example, it uses prime numbers for tables, and division is very, very slow, maybe 100 cycles. So if we make it power of 2, it will be faster. And another possibility to improve is to use better hash functions, because
Yeah.
the current hash functions is not high quality and is not
So
the fastest.
I can tell you about the collisions. So it's about 1 point something collisions on Trumps 3D. Trumps 3D is always the test case I looked at. So I think the
No,
split is-
I mean you need quality hash function because if you going from prime number size to
okay.
power of 2,
Yes,
you need
true.
hash quality number.
Yeah.
For example, high quality hash function should have one property. If you change 1 bit of key, practically half of bits of hash should be changed. That's
Yeah, it's probably
And is that high quality hash function still going to be cheaper than
Yeah, it should be cheaper because FNF is also slow. There are a lot of good modern hash quality functions
so-
for hash tables now, and we use the very, very old one.
so for example the hash function we are using in the iterative hash thing, I think Martin improved this for DVZ by improved by using CRC instructions from the CPU. So there's a great speed up, but probably the CRC is even worse than what we have now in the iterative hash. So I'm pretty sure that the C implementation could be like vectorized or whatever and be made faster. And of
Yeah,
course the value numbering also uses the iterative hash to do the merging of the pieces.
Yeah,
Right.
it can be specialized too for different processors, for aligned, unaligned memories.
Yeah, I mean it's supposed to be host independent, which makes it a more interesting exercise. So we have to compute the same function on each host.
Yeah.
But yeah.
Okay.
But I think for the value numbering, apart from maybe doing more detailed profiles again, so I never saw the division in any of the profiles. The concentration needs to be on the hash, on the memory walks, because there's where somehow all the time goes. By avoiding the work somehow with magic. We've had this in the BOFs, magic. We need more magic.
This is a possibly silly, tangentially related thing. I noticed the return of an unsigned from your mini pass. And first of all, it reminded me I need to finish my patch for the enum to do thing. I think I was wrapping it in a class, so that rather than having naked unsigns in the code. Why, when you have something like, let's say, acts on a function star, say do this, and then return the sort of the state of the I, what's dirty, what needs redoing. Why do we return it rather than storing it as a property of the inside the function struct? Is that an optimization to avoid? Because it seems like a property of the function's IR.
So you're right. We have this property thing, but this was created as an afterthought at some point and abused, misused, and we basically have multiple ways of carrying information, and we should sit down and try to fix that. But yeah, we could set a flag needs Cfg cleanup, because we do have a flag in the loop state needs fix up. So the loop state is different from the function properties, which that could also be merged somehow.
Yeah. I was looking at I read LLVM weekly news, and I saw a commit go by, which was, I think they maybe someone in the room, they reorganized it so that there's a class storing not what needs cleaning up, but more the kind of reverse, what have we got kind of thing, and you sort of you drop in properties rather than what needs cleaning up. And it was an actual class rather than just a set of flags.
So for the specific case of Cfg cleanup, I'm not sure what I would drop. Should I drop? We are no longer in SSA, because there exist regions in the code that are not in SSA. That's I guess the callers need to be aware that if they run this kind of thing, that in unreachable code regions, they are not supposed to do anything anymore. It's for example, the unroller, it unrolls inner loops and then goes to sibling loops, eventually unrolls other inner loops, and after this iteration, before being able to unroll a containing loop of something that it unrolled, it needs to call Cfg Cleanup. But it's an expensive thing because it runs on the whole function. It doesn't run on a region yet. Some obvious improvement, make Cfg Cleanup run on regions. But yeah, anything that modifies the CFG, wrecks the dominator information, and makes it expensive. So it's a way of communicating. Oh, I actually did make a region unreachable. Otherwise, you don't need a CFG cleanup. And yeah, but you're right. There are multiple ways of transferring this information, and well. So if there are no more questions, I have a question. So on the slide, I mentioned I do have this parameter to limit optimistic value numbering to certain loop depth. I actually implemented it that way that it always will optimistically consider the outermost back edge not executable. Well, to be able to remove some abstraction while 0 or something like that. And then keep the innermost n loops value numbered optimistically to be able to handle innermost loops optimistically, and just those in between are basically treated as having an executable back edge and are not iterated. But it was just thought out without any good reason. So any better ideas on heuristics where to limit the iteration? Vladimir, you're smiling. You know everything.
Oh, just a remark. I mean machine learning, but it doesn't work for compilers because it's. I tried machine learning to choose different optimization depending on characteristics of compiled program, and it doesn't work actually. So you need to understand what's going on and to choose these parameters.
Okay, thanks for your attention, and